there is a ring of mass m and it's a non-conducting ring. The charge is distributed uniformly throughout the ring. Its value is q. Then what is the ratio of magnetic moment pm, or sometimes referred to as mu, magnetic moment to angular momentum? What is its value? That's a question. It's a ring of mass m and the charge q. It is rotated with constant angular velocity omega. So these three things are there. So if it is rotated like this, so what all things you should know? First thing is magnetic moment. Magnetic moment, like electric dipole moment, the magnetic dipole moment is current into area. That is one thing you should know. Second thing you should know is, suppose there is a charge q and it moves in a circle. The charge q, and if it moves with the frequency nu, frequency means the number of times it revolves around the center. If it moves, we know that the current I is equal to charge by time. Now the charge is q, it moves with the frequency nu, frequency meaning the number of revolutions it makes in 1 second. Suppose if it makes 1 times in 1 second, then the current is charged by 1 second, because in 1 second it moves only once. If it moves 3 times around this in 1 second, so about this point, this charge q, 3 times it crosses this point. So the total charge flown is 3 times q by n. So if it moves 10 times, which is the frequency 10, then as you see here, the current when a charge moves around a circle is frequency into value of the charge. So this one you should know. So one is magnetic moment is current into area, and if a charge moves in a circle, the current is equal to charge into frequency. And the next thing, omega, the angular velocity or angular frequency, is equal to 2 pi into frequency. And the other thing is, we know that like momentum is mass into velocity, angular momentum is moment of inertia into angular velocity. And for a ring, when you rotate a ring like this, the moment of inertia of a ring I equal to mass of the ring into radius square. These many things you should know to solve this question. So the angular momentum is and moment of inertia into omega. Moment of inertia for this kind of rotation for a ring is mr square, and angular frequency is 2 pi nu. And the current, if a charge moves in circles with frequency nu, then the current is equal to charge into frequency. The magnetic moment is equal to current into area. Let us start with magnetic moment. So magnetic moment, let me call, either you can write it as mu. So in order to avoid confusion, let me write magnetic dipole moment as pm. Pm is equal to current. Current is frequency into charge. So frequency can be written as omega by 2 pi into charge q. This is current into area. This moves in a circle of radius r. Hence, this is current, omega by 2 pi into q, area equal to pi into r square. Then the magnetic moment pm equal to omega q, this pi and pi will be cancelled, into r square by 2. Let us try to multiply and divide by m. So what you will be getting is omega into q into m r square divided by 2m. Now for a ring, the moment of inertia is this mr square. So you can replace this as magnetic moment is equal to I into omega. So I into omega into q divided by 2m. I omega, which is nothing but angular momentum. Hence, this can be written as magnetic moment is equal to angular momentum into charge divided by 2m, which means the ratio of magnetic moment to angular momentum Pm divided by L is equal to charge by 2 times the mass of the charge. So since it is a ring, and when the ring charge is uniformly distributed, so when the ring rotates once, then it is as if a charge q moves around once. Hence here the answer is q by 2m, which is our option C.